Going back and looking at the graph that started this lesson, this whole idea for needing sums, we can still see that there is a problem with trying to find an exact area that is what we call under this curve. Anytime we say under the curve, we mean an area that is between the x-axis and a curve. The easiest way to estimate an area under a curve is to approximate it by using rectangles. And there are a couple ways that this can be done. You can either choose the left endpoint of an interval or the right endpoint of an interval. And whichever point you pick will determine the height of the rectangle. The height is determined by the right endpoint or by the left endpoint. To get a little deeper into what that means, these intervals, we could, if we wanted to, approximate this entire area by one rectangle. So we consider the entire interval from -1 to +3, and we can either pick the left endpoint and find the height, which would be up here. We would get that just by substituting this x value into x. So we know that the height of this rectangle, if we pick the left endpoint, would be y equals 9 minus -1 squared, which is 8. This rectangle would be 8 tall and be 4 units wide. So this rectangle would look something like this. So it would be an 8 by 4 unit rectangle. And what happens here is when you look at this example, you can see that this area up here, it looks like almost a little semicircle, is extra. But this area over here that we have with the rectangle, let me shade the area of the rectangle in black here so you can see the difference. In this black area, we would be counting this extra bit of area that isn't there, but in this blue area, we would not be counting this. But we don't know if these areas are the same, so we cannot get an exact area here. By contrast, if I had picked the right endpoint of this interval, this endpoint, what happens when we substitute 3 into the function? Let's see, 9 minus 3 squared is 0. Oh my. What would happen would be, if we picked this endpoint, and I'm going to use green here to do this. If we'd picked this endpoint, the height of our rectangle would be 0. So we would have no area. That's a problem. Neither of these are very good guesses for an exact area. They're good for approximating, but this isn't going to help. Maybe there's something we can do here to get an approximate answer. So on this page, what I want to do is see if I can get a better estimate of what the blue area is in all of these graphs. So one way to do that is to, increase the number of rectangles within your estimation. So instead of having one rectangle like we did on the previous page, let's divide the interval into 2 equally spaced intervals. And from here on out, I'm going to simply concentrate on the left endpoint method to simplify this process. So now, a couple things to note is that with this first graph, we will be using 2 rectangles. And if we're using two rectangles and we're trying to find the area of rectangles, we should probably know how wide each rectangle is. And to make the math really nice, we are just going to make the width of each rectangle the same. So since we have an interval that we're looking at of 4, if we have two rectangles, that means we're trying to find the area of a rectangle with a width of 2. And that's because we have an interval of 4 and we're dividing by the number of rectangles. So the left endpoint for this first interval happens at -1. So if we follow that all the way up to where the actual function is, that's what gives us the height of this rectangle. So we have a rectangle that is this tall and 2 units wide. So there it is. So we have this red area of this first rectangle. The next rectangle, if we look at the left endpoint of the interval from 1 to 3, the left endpoint is at 1, and if you follow that all the way up, that means the height will be right here, because this is where the function is. So this rectangle will also be that tall and 2 units wide. So we have all of this red area. It looks like we're still overestimating by this area here, and we're still underestimating a little bit by this area here. Will they offset each other exactly? Probably not, because we're dealing with a curved graph of a function. All right, let's see what happens if we increase the number to 4 rectangles. When you increase the number to 4 rectangles, the width of each rectangle would be the width of the entire interval, which is 4 units, divided by the number of rectangles we want. So this would be 1. So each rectangle is 1 wide. So when we look here, we're going to divide this interval into 4 equally spaced intervals. So again, starting with the left side of this interval, it looks like if we follow this up, we hit the graph right there, and we're only going to make this rectangle 1 wide right now. We're making the width of each rectangle smaller. We're increasing the number of rectangles we have. So there's that one. If you look at this little interval between 0 and 1, the left endpoint at 0 takes you all the way to the top of the graph. So we'll start here, go all the way up, and our rectangle will be 1 unit wide, and we'll follow that all the way back down. So with this third interval down here from 1 to 2, we're going to follow that on the left endpoint 1 all the way up to the graph, which is right here. We're going to make that rectangle 1 unit wide and follow it back down to the x-axis. And in this last interval here, between 2 and 3, we're going to take this all the way up to the graph. Come out here, and there you go. So this is starting to look a little more accurate, it looks like. We're overestimating in these areas here, and we are underestimating the area over here. But it looks like that we still have a large amount of overestimation compared to the underestimation. All right, let's try it one more time with 8 rectangles. When you do it with 8 rectangles, and you are looking at equally spaced intervals along the x-axis, you'll get something that looks like this. Each rectangle here will have a width of 1/2 because the entire width is 4 and the number of rectangles we have is 8. And it is so much easier to find the area of a rectangle if we can keep the width a constant like 1/2 or 1 or 2. And we're doing that, we're just taking the width of the interval and dividing by the number of rectangles. One thing you can see is that the amount of overestimation that we're getting now is much less than what we had in the previous two examples. The amount of overestimation here in this first example is really large. The amount of overestimation here in the second example is getting smaller, and the amount of overestimation here is becoming much, much less. So it seems like the number of rectangles, as it increases, the closer and closer and closer we get to the exact area. There's a theorem that states no matter which endpoint you use, if the number of rectangles approaches infinity, you will get the same exact area. So how this relates to you and the sums that you've seen is that n is the number of rectangles we're using to approximate an area. And so what I'm going to do now is to go through this example, and then at the very end, I'm going to substitute 10 in for n, I'm going to substitute 100 in for n, and I'm going to substitute 1000 in for n. And we will see what happens to the sums as we substitute these numbers in here. Going through this entire process, we get a final expression of -6 plus 2 times n plus 1 over n. And it turns out that when you substitute n equals 10, or 10 in for n, in this expression, you will get -4.9. And if you substitute n equals 100 into this expression, you will get -4.99. And you might see the pattern already, but if you substitute 1000 into this expression, you will get -4.999. And what happens is when we're summing up all of these terms from 1 to n, and we're increasing the number of rectangles from 10 to 100 to 1000, these numbers we're getting back for our sums, these are areas. So when we had 10 rectangles, we got an area that was -4.9. So that's close. But if we increase the number of rectangles to 100, we get even closer to the exact area, -4.99. And 1,000 rectangles, we get even closer to the exact area, -4.999. Now you might be guessing that as n goes to infinity, that tells us the sum will go to -5. This is exactly the idea of what a limit is. So in the next couple examples, you will see some limits as n goes to infinity of some summations.